Okay, suppose the family has 2 children. We want to find the probability that both are girls, given that the elder child is a girl. And second, find the probability that both are girls, given that at least one of them is a girl. Well, how many possibilities would we have in total? 4. You can write it out. So boy, girl, boy, boy, girl, girl. It's one way of doing it. What is the other way in terms of counting? Tree would work in terms of counting without trees.
The formula you're talking about.
Yeah. How many possibilities would we have for the first child? 2. How many for the second? 2. In total, 2 times 2. 4. Good. We could do this as a conditional probability problem. So, probability that both are girls, given the elder child is a girl. I could call that A, I could call that B. Probability of A intersects B divided by the probability of B. So what is the probability that the elder child is a girl? %. 50%. How did you get that, Mary?
Well, I mean, I heard Casey, but also it's just kind of like logic. There's only 2 options.
There are 2 options, right? 2 out of 4. And what is the probability that both are girls and the elder child is a girl? 1 over 4. So there is a 50% chance that both of them are girls, given that elder child. So it's 50-50. I mean, we could have guessed that, right? If, both of them had to be girls, and I said one of them is a girl, I'm not giving much information, elder child is a girl, then there's a 50-50 chance for the second one. It's either a boy or a girl, 2 possibilities, but since we want both girls, 1 out of 2. Does that make sense? So both of them are girls, given that at least one of them is a girl. Well, how do we do that? Same, I'll call it A1, A2. Probability of A1 intersects A2 divided by the probability of
A1
A2.
Oh, my brain was like, I was thinking like A1 is row 1 and A2 is row 2. Yeah, that's all I wrote down on my paper, and my brain is like, what's the same, right?
So what is the probability of A2? At least one of them is a girl. 3 out of 4. what is the probability that A1 intersect A2 happens? Both of them are girls, and at least one of them is a girl. 1/4. I mean, of all the four, only one of them would satisfy both of those, you know. So that would be 1/4. So the probability is 1/5. So this is a simple case of, Bayes rule, bringing some evidence, useful evidence, then the probability, is going to change. Not always, but most cases. Yeah. Okay, same problem. So 2 children, we want to find the probability that both are girls, given that at least one of them was born in winter. We're assuming that there are 4 seasons, and we assume that the gender is independent of the season. At least one of them is a girl born in winter. That will ruin everything. Born in winter is a girl, it has to be a girl. So probability that both girls, given at least one girl is born in winter, is equal to the probability that both would happen divided by the probability of B. So first we've got to find probability that at least one girl was born in winter. Well, what is the complement of probability of B? Don't tell me B complement, even though it's correct. The probability that at least one girl is born in winter, what is its complement? None of them were born in winter. Or you can say both girls were not born in winter. Well, how do we find that probability? Well, we could also use complementary rule. What is the probability that a girl born in winter? Well, in terms of seasons, what is the total number of possibilities that we have? 4. In terms of gender, how many do we have? 2. So total we have 8 possibilities, right? Now we're saying we want to know a girl that's born in winter. So this is total winter girl. How many would we have for season? 1. How many would we have for girl? 1, because it's a girl. So 1 times 1 is just 1. So what is the probability of a winter girl? It's 1 out of 8. Right. There's a probability that the girl that a girl is born in winter is 1/8. What is the probability that a girl was not born in winter? 7/8. So 7/8 is 7/8. 1 minus 7/8 squared. Yes.
That's the probability that none of the girls were born in winter. That would be the probability that none of the children were born in winter. were girls born in winter? Is it none of them were girls born in winter, or none of the girls were born?
None of the girls were born in winter.
Well, that's taking into account boys as well, isn't it? With the age.
Yeah, that's why we have 8 possibilities. So what is it?
Can you explain that, this okay?
So, yeah, I'm not sure that 7 out of 8 would be that none of the girls were born in winter.
Okay, total we have 8 possibilities by 4 seasons,
So that's including boys, the age.
right, and 2 genders. And none of the girls were born in winter.
That should be 3 out of 4 times correct for it.
So none of the children were born in winter.
Yeah,
Yeah.
were girls born in winter.
All girls born in winter. So
None of the children were girls born in winter would be 7 out of 8.
Can you draw a tree diagram?
well, that's what I was talking about.
The way it was worded does not mean the same thing.
None of the children,
Were girls born in winter would be 7 out of 8. None of the girls were born in winter would be 3 out of 4.
well, I think it's the semantics, but this is what I was
Well,
trying to.
semantics do matter in probability, no?
Yeah, I agree. So none of the girls were born in winter. None of the children were born. Okay, this is what I was talking about. So 1 minus 49 over 64, which is 64 minus 49 over 64, which would be 15 over 64. Okay. If you want to draw a tree, it's the same, 4 seasons: fall, winter, summer, spring. Yes? Yeah. And then you've got male or female, male, female, male, female, male. Right? 8 possibilities. Let's see, what is the numerator? Both of them are girls and at least one girl born in winter. So since we have both of them to be girls, we are given that the gender of both of them are girls. And at least one girl is born in winter would make that particular event independent of this event because of the assumption that the gender would be independent of the season. So I can simply break this apart and write it as probability both girls multiplied by the probability at least one girl born in winter. Once again, since gender is independent and I know both of them are girls, I could simply say one child born in winter. So what is the probability that both of them are girls? That's from the previous problem. We could use the same thing. You have 4 possibilities. It would be 1 out of 4. We just need that probability that at least one girl, you could change it to child because we know the gender already, both of them are girls. So you could say at least one child born in winter. Let's see if you can do that. Let me put it in parentheses. Since we know the gender, you could call this as child. I'm able to split this up and write it as, independent because I gave a statement that the gender becomes independent or is independent of the season. And also here, since I know that both of them are girls, whether I call it a girl or a child, doesn't matter. It becomes a child because I know that they are girls, common overlap. So that would be 1 minus the probability that none of them were born in winter. Well, what is the probability that a child was not born in winter? You have 4 seasons, only one of them is winter. So this would be 3/4 times 3/4. What does that equal to? 15 minus 9, 7/64. Yes. So the final answer for that would be that value divided by that value. 7/15.